So today we're going to talk about some properties of definite integrals that will be absolutely essential, especially as we move forward into the second part of fundamental theorem of calculus. So suppose that we're given the integral from a lower limit a to an upper limit b of an integrand called f of x with a dummy variable of x. If you like, you can split apart this limit, not directly from a to b, but take a pit stop at an intermediate value of c, then pick up again and add on a second limit going from c to b. If you add these two integrals together, the sum total will be the same as if you just integrated directly from a to b. And as well, if you decide not to go from a to b, not from left to right, but to go in the opposite direction, you can reverse the order of these limits and put a on the bottom and b on the top at the cost of flipping the entire sign of the result, putting a negative sign on the outside of the result. Let's use these two properties of limits to answer the following exercise. They say, for some unknown integrand, let's call it f of x, we have a couple of facts here. One, we know the integral from -7 to 3 of f of x is equal to 20. Next, we know that if we take the integral from -7 to 1 of 4 times f of x, the result is 16. What then is the integral from 1 to 3 f of x dx? Now the first thing that I would like to do is I would like to deal with this second statement, because this is the only statement at the moment that is telling me about the integral not of f of x itself, but of 4 times f of x. Now remember that we have this constant multiple rule for integration, which says that constant multiples on the inside of an integral can be pulled to the outside of an integral and done at the very, very end of the integration. This allows me to divide both sides by 4 and get a statement that's more directly talking about the original function f of x, the integral from -7 to 1 of f of x is equal to 4. Now, let's get a little diagram going. We have this function here. Who knows exactly what it's doing, but it's working on the region from -7. In fact, let's forget the x-axis, rather forget the y-axis. -7, 1, and 3. Let's say our function looks a little bit like this. What we have been told is that this complete full area, all the way from -7 up to 3, this full area is equal to 20. And if I take this narrow band from -7 to 1, then this band is only worth 4. So if that full graph has an area of 20 underneath it, and this little portion from -7 to 1 has an area of 4 underneath it, that means that this portion from 1 to 3 must have an area of 16 underneath it, In other words, the integral from -7 to 1 of f of x, which is here 4 in the beginning, plus the integral from 1 to 3 f of x is equal to the integral from -7 to 3 f of x, and replacing the values that we do know, 4 plus the unknown integral is equal to 16, and therefore the unknown integral is equal to this 16. So here, some integral properties can be used to split apart or to combine definite integrals in many different ways, and we'll be using this a lot in the next section.